All right, well, thank you very much. Um, so today we're going to cover Tire NVH, including all the current trends and challenges and various solutions for Tire NVH. And we're going to look at both interior tire and road noise, as well as exterior tire noise. We'll also be looking at both experimental methods and analytical CAE methods for Tire NVH. But first, we're going to introduce HBK and VI-grade. So over to you, Rabah.
Thank you, Dave. So we give a brief introduction about HBK. We are a global powerhouse in test and measurements. We are the results of the merger between Brunel and HBM, and that brings us to our portfolio a testing solution for load, strength, durability, torque, in addition to sound and vibration from Brunel. We also have a division taking care of electric power testing. I'm from the services department. Our team is a global team located in Asia, Europe, and North America. I'm located in North America. And our team specializes in consulting services. And we help our customers face their challenge with noise, vibration, force, strain, electrification, using the best-in-class solution from HBK.
All right, thank you. So VI-grade's mission is to accelerate automotive product development by bridging the gap between data and user sensory experience. VI-grade produces a market-leading suite of simulators and simulation products. HBK and VI-grade are sister companies, and we work very closely together. For NVH, VI-grade provides unique technology for assembling virtual NVH prototypes and experiencing sound and vibration data interactively in driving simulators as an integrated part of the development process. Let's take a moment and examine what we will be discussing today, Tire NVH. NVH is automotive sound and vibration. NVH is one of the main attributes controlling and delivering vehicle refinement and brand DNA. Consciously or not, people make decisions and form opinions based on the sound and vibration they perceive from the vehicle. Tire NVH can be broken into three main areas. Interior structure-borne sound and vibration. This has many aspects and includes many phenomena. Ride comfort or secondary ride, vibration, booming, and other manifestations of sound and vibration fall into this category. Generally speaking, interior sound and vibration due to structure-borne tire and road inputs falls below 800 Hz. Typically, we are looking at vibration at the seat, steering wheel, and floor pan, though there can be other important vibration receivers or points of interest. Sound is generally characterized at the driver or passenger's ear positions. Interior airborne sound is generally thought of as the tire tread noise that radiates directly from the tire or the tire contact patch through the vehicle body to the interior. Typically, this airborne sound is mostly above 500 Hz. Exterior airborne sound is the sound radiated from the tire and tire road contact patch to an exterior microphone or observer. All of these are ultimately driven by the road surface, the characteristics of the tire road interaction, and the surface itself, which can be smooth or rough or coarse or have imperfections or transients or impact generating events. There are many challenges in Tire NVH. First amongst them is the effect of EV powertrains on overall vehicle NVH. Tire or road noise is becoming the dominant source of sound inside the vehicle cabin now. Another significant challenge is the increasingly stringent requirements for vehicle pass-by noise, especially in Europe. As the legislated levels for pass-by drop lower, the tire noise becomes a critical factor in meeting and passing these regulations and requirements. With a shift towards EVs, vehicle architectures are changing, which has a big effect on how tire sound and vibration are transmitted to the interior of the vehicle. Lightweighting is a topic that's been around for a while, and it's completely relevant today. Generally speaking, reducing mass means easier noise transmission and less mass budget for sound package material. Range in general is a great concern, especially for EVs. Traditionally, tires that are good for increasing range have not necessarily been good for NVH. There have been some trade-offs here. And autonomous vehicles provide an additional challenge. These provide a completely different occupant experience where the occupants have more attention available to focus on the sound characteristics of the car, with the tires being the dominant source of noise and vibration in the vehicle. That means occupants are more likely to focus on sound and vibration of the tires. So what are the goals for Tire NVH? One goal is to be able to set targets for tire-generated sound and vibration. Another is to assess the performance of existing tires on an existing vehicle. This could be as a complete system with the physical tires on a physical vehicle on a test track, or it could be virtually swapping tires between vehicles. Assessing sound and vibration on virtual vehicles using measured source levels of a physical tire could be another goal. And assessing the sound and vibration of virtual tires on a virtual or real vehicle could be another goal. Ultimately, we want to make better decisions about our tire designs and specifications faster and with confidence. When we look at how we characterize Tire NVH, we utilize experimental methods, analytical methods, and hybrid methods. We will examine all of these in this webinar. Likewise, with data evaluation, we can evaluate using objective methods with charts and graphs and numbers, or we can evaluate with subjective methods, experiencing the sound, the tire sound and vibration data.
All right, and to illustrate this, let's look at an application case for structure-borne road noise. But first, by describing the process behind actually. So for a source path contribution analysis, tire noise is actually a very complex phenomenon. It includes multiple sources at the tire and road interface, the noise that is generated directly at the tire due to the air pumping at the thread, standing waves into the tires, wall vibrations as well. Now, these sources propagate to the driver's ears, either through the air around, that's the airborne path, or through the structure. So the tire wheel, the tire road interaction creates vibration at the suspension that propagates and generates basically forces at the body attachment point. And so with those, then we characterize then the airborne and structure-borne path. Now, for any noise and vibration, those can be, we can use the model of the source, path, and receiver, or source path contribution. We'll start with the noise and vibration sources that results from the tire road interaction. We have the forces generated at the body attachment point, and we have the noise that is generated at the tires. Now, those can be measured or potentially simulated, and then we can use those to characterize them. The second part is the transfer from these sources to the receiver, whether inside the vehicle or outside. And there we can, and then it includes multiple paths. So we have the path through the air going around the vehicle and then propagating through the body panels. And we have the structure-borne path from the body attachment point, generating vibration of the panels that results in a sound that is perceived by the receiver. And then, of course, we have the coupling between the air and the structure, or for exterior noise, we have then the air-to-air transfer functions. And as an output, and if we combine those sources and the transfer function, we get then the sound that will be perceived by the driver or the occupant inside the vehicle, but also on the outside, and typically this would be for a receiver at the pass-by location. We've talked about noise, but actually the same principle can be used for vibration, and in that case, then the receiver will be the driver or the passengers, and the target can be defined at the different tactile locations. To illustrate this, let's look at an example that we worked on with the team at Hexagon MSC Software. The goal here is to synthesize the structure-borne road noise starting from a CAE simulation model. So the team at Hexagon performed multi-body simulation in Adams. The model included a tire model to represent the tire-road interaction, included as well flexible bodies for the cab and the frame. The application case is a pickup truck here. The vehicle was driven over different road profiles defined by a PSD curve from an ISO standard. And out of the simulation, they calculated the cab attachment forces at the attachment points for multiple conditions, and each condition corresponds to a vehicle speed. The team at MSC Software also developed an acoustic model, coupling the structural finite element model of the cab with an acoustic model of the cavity to calculate transfer functions. And the team at HBK and VI-grade then gathered these inputs, so all the forces at the different attachment point for the different vehicle speed, combine them with the transfer function to generate the structure-borne noise at the driver's ears. And then those information then has been translated into a model that can be evaluated in the VI-grade and NVH simulator. We illustrate this, but when doing this, it's important to have the proper contextual sound, including not only the attribute that we have simulated, but also the remaining attribute, whether it's powertrain sound. Here we had the tire noise as well, the airborne contribution, and wind noise. So we'd be looking at some results at a high speed, and wind noise will be becoming dominant. And so it's important to capture that in the evaluations as well. And this data was then coming from measurement data here.
All right, so this is a good time to look at how we can evaluate NVH data efficiently. Many types of engineering data and CAE analysis can be adequately expressed and experienced and understood visually. So decisions can be made by looking at a computer monitor. NVH data is a bit different. We get lots of great information from testing and analysis and simulation, but these results are typically in the form of plots and graphs. NVH data cannot be fully expressed or experienced or understood by plots and graphs and numbers and visual means. Numbers, plots, and graphs are very useful, but they don't answer questions like, does it sound good? Or is it better than this other vehicle? Or what does it sound like? So to address this, we created our NVH driving simulators to enable the experience of all the various types of sound and vibration data together in an interactive real-time driving simulator. We developed the NVH simulator technology to enable the experience of sound and vibration data. The VI-grade NVH simulator software and simulators enable the full understanding of NVH data by allowing you to experience the sound and vibration data as actual sound and vibration. Virtual vehicles composed of measured data, simulated data, or a combination of both can be driven interactively, just like a real car. Individual parts of the sound can be independently controlled, turned on and off, filtered, and modified. Different vehicles, components, and configurations can be compared back to back instantly. The NVH simulator is an incredibly useful tool for understanding and communicating sound and vibration data, and for facilitating NVH decisions rapidly and with confidence. While NVH simulator models can be created entirely from measured data or entirely from CAE data, the vast majority of NVH simulator models and virtual prototypes are hybrid models of CAE and measured test data. Often, test data will be used to provide context for components outside the scope of the immediate evaluation task, or for data in frequency ranges that are outside the scope of immediate evaluation and analysis. For example, say road noise is being analyzed. In this case, we have some data from the Altair NVH director, which is a combination of simulated loads at attachment points and transfer functions. A detailed finite element model of a vehicle and a high quality tire model are used to generate road noise levels for the vehicle, but only up to about 200 Hertz. This data can be accurately generated and played back in the NVH simulator, but listening to sound up to 200 Hertz with nothing else above that is not so realistic. So a good solution is to use surrogate road and wind data from a similar vehicle, perhaps even modified slightly to match the future vehicle intent, and apply this above 200 Hertz while using the detailed analysis results below 200 Hertz. All right, so we're going to show a video in just a minute. And this is the results of the hybrid model that I just mentioned. An NVH simulator model enables us to listen to the results. Again, here we have an FE model, FE results used to calculate the suspension attachment point forces due to tire road inputs, and transfer functions were applied to those suspension attachment point forces to create the sound inside the vehicle. Due to the nature of the model, results up to about 200 Hertz are available. We can listen to the sound up to 200 Hertz. It sounds kind of artificial though, it sounds kind of muddy. To put it in the correct context and make it sound realistic, we take some measured full bandwidth road noise recorded on a similar vehicle, high pass this at 200 Hertz, and play it along with the sound created from the simulation results. So right now, we're gonna play a short video showing this. All right, so with that, we can confidently assess the impact of the low frequency sound in a realistic context of natural sounding, complete vehicle soundscape. All right, Rabah, back over to you.
All right, thank you, Dave. All right, and we'll cover now the road noise synthesis from blocked forces. So we illustrate here how we can use measurement data to characterize the sources at the tires, combine them with transfer functions, which can be either simulated or measured. In this case, we will use simulation data, and we'll demonstrate how we can create a virtual vehicle that you can then experience in the simulator. We'll first introduce what are the blocked forces. So when we have a source of noise and vibration operating and attached to a receiving structure, we can characterize the source by using the free velocity of the source. That is the velocity we would measure at the attachment point if the source was hanging in a free condition. Now, the blocked forces characterize also the source, but there corresponds to the forces you would have at the attachment point if you were to attach the source to an infinitely stiff structure. Now, both these, free velocity of the source, blocked forces, only characterize the source, and they are basically equivalent. And now we can use this property and turning off the source and just apply the blocked forces at the interface, and we would get the same vibration data at the interface, and so this would be then equivalent. And that's actually the important property of the blocked forces, is that it's characterized the source, and it can be then if it's applied at the interface, it generates the same vibration as if the source is operating. And now we can use those properties actually to replace the case that we have to consider with tires operating on a vehicle by a case that we can test, which corresponds to tires tested on a stand, where we can characterize the blocked forces and then apply those blocked forces on an assembly. And those blocked forces then are only characterizing the source, and they are independent of the receiving structure. That's an important property, because once we have them characterized, we can reuse them for different vehicles. Now, how can we characterize, how can we get those blocked forces? Well, we can follow the theory and develop an infinitely stiff test rig and measure them. Now, it's maybe sometimes impractical to do so, but we can also use the properties of the blocked forces to characterize them in situ. For this, we can instrument the system with sensors, as we would do in a source path contribution analysis or transfer path analysis, and measure transfer function as well, and use an inverse force characterization to back calculate the blocked forces. And in this case, we don't have to disconnect the source from the receiver. We'd have to look at the assembly. That's per the properties of the blocked forces, and that's what actually makes it easier for the test, but also let us use those forces independently from the receiving structure. Let's illustrate this with the application case we worked on here. So at HBK, we have a tire test stand. It's a test stand we can install in our NVH chassis dyno to perform a tire test. We can use the smooth rolls, or we can install rough shells on the dyno, and then we can measure the sound and vibration on the dyno. We perform the test at a constant speed. We can also do run-ups if needed, but to characterize the blocked forces, we've used multiple tests at a constant speed, and we can adapt the preload on the tire as well as the inflation pressure to when performing the test. So we performed all of this. We also measured transfer functions on the test stand. And for this, we had instrumented the test stand with vibration sensors, but also strain sensors to capture the broad frequency range from the very low frequencies to higher frequencies with the accelerometers. We also had microphones that we can use and to characterize the airborne noise sources. For structure-borne, we are looking at the forces at the wheel center, and those are defined in 5 degrees of freedom. So we have 3 translation and 2 rotations. Now, it's straightforward to measure the transfer function in the translation direction. It's more challenging, of course, for the rotations. So for this, we have used a virtual point transformation method. What it does, it's basically assumes that the hub interface is perfectly rigid, and we measure translation transfer function at multiple locations around the wheel center with different offsets, different directions. Now with this, we are inputting a force, but also a moment due to the offset, and we can build then a matrix for coordinate transformation between the forces, 5 degrees of freedom forces that we are looking for, and the forces that we technically applied. And we can then assemble a large matrix by repeating this over a certain number of points, 10, 15, and then we can then back calculate then the transfer function for the 5 degrees of freedom, assuming that we have then here a rigid connections. And so we perform this work and then characterize then all those blocked forces. In parallel, we worked with the team at Hexagon MSC Software to develop a finite element model of the vehicle to then characterize the transfer functions. So the team created a finite element model of the structure for a sedan vehicle, created an acoustic model of the cavity. They also created a pearl-elastic material model for some of the trim subsystems, and they used this to characterize the transfer functions from the wheel centers to the driver's ears. They repeated the simulation, of course, for every single wheel center and predicted the results up to 400 Hertz. They've done the calculation into the model domain. Now we've used all these results. So the forces that we had identified from the test stand measurements, the transfer functions received from the team at Hexagon MSC Software, and then with this created a virtual prototype for sound evaluations. As they've explained, so we complemented the structure-borne noise with measurement data for the airborne road noise, powertrain as well, even though it's maybe less important here, and then wind noise when we reach the higher speed as well. Now with this, then we can then create now a tire database and repeat this process for different vehicles. In the future, we'll also be looking at how to use then the airborne sources that we have characterized from the same measurements. Before that, actually, we had already worked on the airborne noise, and we had used a different approach. So this example will demonstrate how we can also then develop a virtual prototype for airborne road noise to look at different options for sound packaging. We had a vehicle and performed a baseline measurements, and we decomposed the interior sound into structure-borne road noise, airborne tire noise, wind noise, and powertrain noise. And our main interest here is on the airborne tire noise. We worked with a team at ESI, and they developed an SCA model of the vehicle and used it to try to optimize the sound package. They created different alternatives of sound package and then looked at the comparison between those sound package and came back with basically a frequency dependent filter. That's a filter that corresponds to the difference in transfer function when they change the sound package compared to baseline. And we use those filters and apply them on the sounds that we had decomposed from the measurement data to be able to oralize and evaluate subjectively what is the effect of the sound package changes. This was done on the front and rear tires separately, and helped then guide then the sound package optimization. And again here, one key criterion and added value of doing so is actually that when we are able to experience the sound, not only it helps makes an informed decision, but it also helps justify them and defend them in front of decision makers. With this, I'll turn it to Dave.
Yeah, great. All right, so before moving on to exterior tire noise and other aspects, I wanted to take a minute and introduce the NVH Simulator family. The desktop NVH simulator enables us to drive and experience virtual prototypes and understand NVH in a natural way. Whether simulation data, measured data, or a combination of both, the desktop NVH simulator allows you to drive interactively and switch instantly back to back between vehicles or designs, turn on and off component parts of the sound like wind noise or road noise or powertrain, modify parts of the sound in real time with multiple types of filtering and sound modification tools. The NVH Simulator software is at the core of all of the NVH solutions and is used in all versions of the NVH Simulator. There are more than 50 desktop NVH simulators installed at customer sites worldwide. The desktop NVH simulator focuses on the noise part of NVH. Vibration is another important aspect of the overall vehicle experience, especially in the realm of tire NVH. While we can do quite a bit of NVH design and evaluation on the desktop, for vibration we need a bit more. The compact NVH simulator enables us to experience vibration in the same way we use headphones to experience sound. The compact NVH simulator is the first simulator of its kind in the automotive industry. The key focus of this simulator is calibrated, integrated vibration and sound, delivered in a system which can simulate any vehicle regardless of its inherent vibration characteristics and dynamic behavior. 7 independent degrees of freedom of vibration are delivered to the driver. So vibration is delivered to the seat in the vertical, the lateral, and fore-aft directions. The steering wheel has vertical and lateral vibration components, and the footwell or heel point has vertical and lateral vibration as well. This combination delivers vibration to all driver touch points in the vehicle, providing a very realistic and accurate experience. Of course, the vibration is calibrated and equalized, so the exact vibration stimulus which simulates the vehicle is delivered to the driver. Sound, of course, is also a critical piece of the evaluation experience with the vibration, so highly accurate calibrated sound is provided through high quality headphones and a subwoofer. It's really a combination of the sound and vibration that delivers the unparalleled NVH experience. Anything we can do on the desktop, we can do on the compact simulator with the addition of multi-point calibrated vibration. For many years, we've offered the static NVH simulator, or sometimes referred to as the full vehicle NVH simulator. Several of these have been built and delivered to customers and are in use today. Like the compact NVH simulator, the static simulator adds calibrated multi-axial independent vibration at all driver touch points, but built into a shell of a complete vehicle and surrounded by an expansive visual display. This is one of the most immersive ways to experience NVH data. The NVH simulator is capable of easily accepting data from many different sources and many different formats. Time data, frequency response functions, and other types of data are easily utilized in the NVH simulator. The NVH simulator accepts measurement data from a wide variety of sources, all common file formats. You'll probably notice that as Rabah has gone through and continues to go through the various examples today, several different CAE providers are mentioned. CAE results and data are vital components of NVH virtual prototypes. We've worked together with several CAE suppliers to make it easy to bring CAE results into the NVH simulator and utilize these in virtual NVH prototypes. All right, so back over to you, Rabah.
Thank you, Dave. We move now to the automotive exterior noise. The pass-by regulations are becoming ever more stringent. That's driven by changes in Europe and in Asia, with 2 dB reductions every 4 years. So we are in this range. The next reduction is expected in 2024. Now, in addition to that, there is a change in driving conditions to align with urban noise, and that increase the tire noise contribution. And we also have additional constraints to avoid any defeat device like the ASAP, for example. Now, of course, for the automotive industry is constantly pushing for a reduced time to market, and that makes things even more complex. And because of that, we believe that vehicle engineering for exterior noise will have to be front-loaded to avoid delays and expensive countermeasures, as we are sometimes experiencing with interior noise. To further illustrate this, we've taken here results from a study that was performed in France, where they looked at the sound, the pass-by noise level when vehicles available on the market, I think it was in 2016, were tested against the previous standard and the current standard, the upcoming one. And they reported in the different levels. That was back in 2016 to 2020 and then 2024. And we see actually that out of all the vehicles that were certified to be on the road at that time, only 8% of the vehicles were meeting the 2024 pass-by noise requirements. Now, what is actually the main driver into this? It's actually tire noise can be one of the dominant contribution. And this is due to the fact that the testing conditions have changed, and we'll have to have then full thread tires, and that will increase the tire noise. Now, with the current move towards electrification, the pass-by noise challenge will still remain very valid because EVs have, of course, a different torque curve, and the test is at a full throttle. And for electric vehicles, we may reach an exit speed on a pass-by track, which is much higher than a vehicle with an internal combustion engine, and that can make then that can increase then the tire noise. We have actually here results of a source pass contribution analysis project we performed for pass-by noise, where we looked at the different contributions, whether it's the engine, intake, exhaust, or tires. And we see actually that for one vehicle that we had tested here in third gear and second gear, tire noise is actually the dominant contribution. And so that explains and justifies why actually the engineering process for exterior noise to be able to meet the regulations will have to be adapted. And hopefully we are here to help, and we have state-of-the-art solution that can then help you face this challenge. We illustrate here some of the solution. We'll talk also about them in the upcoming slides. We provide solution for, of course, field pass-by testing. We provide full systems. We also provide solution for indoor pass-by testing, but also solutions for source identification that can be then quite important, not only to characterize the tire noise emission, but also investigate the pass-by noise levels. We have here an example of a list of example projects we have performed recently for exterior noise. They include north-south identification using acoustic arrays, indoor-outdoor pass-by noise correlation, source pass contribution for pass-by noise. The goal here is to decompose the pass-by noise level into contributions from tires, exhaust, intake, engine, and then identify actually what is contributing the most and look at options to reduce it. We've also done additional work to validate smaller chassis dynos than the one required by the ISO standards, and still validate the results and allow them to and be able to use them for engineering purpose. Let's illustrate some of the solutions. For noise source identification, we typically use acoustic arrays, and we've been performing a test at tire level on a single tire, but also on a vehicle level. We can use a solution for holography and then to characterize what is the noise generation mechanism. We also have a solution for conformal mapping, and that help characterize the surface vibration. So it's a non-contact way of characterizing the surface vibration and identify the noise sources. It's an extension of the holography, but in using a non-planar surface. If we're talking about single tire, we are also, we mentioned actually our tire test stands. So the ISO committee is working on a new standard for the tire sound emissions of using an indoor test methods. That's the method of a drum. So we are equipped to perform this. We'll be ready when the standard gets released. And this method actually seems to be very effective, with a correlation with exterior noise within 1 dB. For pass-by noise, actually, this technique could potentially be extended, and the goal would be to use sources that we can then characterize at the tire test stand level using our solution for source pass contribution, and then propagate them to the pass-by noise receiver using the technologies that are available in our solution for indoor pass-by. And the goal here is then to front-load the pass-by noise engineering with a focus on tires here, and potentially also use CAE simulation data. For example, if we were to look at the effect of liners or modifications on the vehicle that can lead to a potential reduction in the pass-by noise levels. And results published actually in analysis performed by some material providers, for example, have shown that there is some levels to be a couple of dB actually. It can be grabbed there by optimizing the liner and the vehicle treatment, and not just the source. Now, to wrap up actually the presentation, we wanted to show some additional work that we have performed, just to describe the extent of the solution we provide at HBK Sound and Vibration Engineering Services. We've also developed an offering to support the development of tire CAE analysis. And this starts with the characterization of the tire properties and material properties from test, and so we can support those and provide them to our customers or CAE partners to then characterize then the tire material model. In addition to that, then we can then perform a test to validate the tire model, and that can be a stationary test looking, for example, at the contact patch and validate CAE simulation results against reference measurement, but also dynamically using, for example, an experimental model analysis. Once this is done, we can even look at the noise radiation. So again, use the acoustic camera, for example, to compare and validate the noise radiation. I'm sorry. Let me share the screen again. There we go. All right, so we can look then at the switch here. All right, and we can look then at the noise radiation and validate and use the measurements to validate the CAE simulation result. And I would actually cover here the tire tread noise application. As a final slide, I actually wanted to show, for example, some examples of results here, and we picked a model analysis that we've performed recently on the tires, on loaded tire, and then we showed in here animate a couple of the modes that were identified and results that can be used then for CAE simulation model validation. With this, I will turn it to Dave for our conclusions.
Okay, great. So in conclusion today, we have reviewed the many challenges associated with Tire NVH and shown a number of examples. Tire sound and vibration is a broad field with many different technologies employed to measure, predict, and simulate the impact of Tire NVH on the overall perception of the vehicle. HBK Sound and Vibration Engineering Services are experts in the various technologies involved and can provide benchmarking, target setting, validation testing, method development, CAE integration, and many other services and solutions. And VI-grade provides a complete, accurate, proven, and open set of solutions to enable you to design, simulate, and understand Tire NVH challenges and solutions faster, and accelerate product development. VI-grade NVH simulator solutions help you make better decisions faster with more confidence by bridging the gap between data and sensory experience. All right, so that brings us to the end of the presentation. For a more in-depth look at the solutions you saw here today, contact us at info@vigrade.com, or you can also visit the web or just scan the QR code on the screen.